Let's talk about how to solve one of the biggest problem with current retrieval augmented generation systems. Most of these systems rely on semantic similarity that tries to identify chunks that are most similar to your query. However, this results in some serious problems. Chunking basically loses global context. You cannot do cross-document references and document dependencies. In order to solve this issue, I am building an open source project that replaces simple semantic similarity with how humans look for information in a large corpus. I'm calling this exploration rather than simple retrieval. Let me show you an example of how this system works. Now, I have a very complex query. For a query like this, a normal retrieval augmented generation system will probably fail because it doesn't have enough context, especially if the information that you're looking for is contained across multiple different files. Now, here's how it works in our case. The agent first read the closing checklist document. Then it says the closing checklist indicates that the due diligence report is a key document. And then it started reading that document. And based on all that exploration, here's a very detailed answer that we get at the end. So let me explain how this whole thing works. One of the biggest problems with the current systems is cross-references in documents. And this happens in real-world documents. Let's say if you're working with legal documents or insurance documents, there are cross-references. The problem with chunking is that it loses that context. And even though the information is going to be present in your documents, the way semantic similarity works is that it simply looks at a few chunks that are most similar to your original user query. And the RAG or retrieval system will completely ignore these cross-references. A solution to this is agentic-file-search. Now, this is different than agentic RAG or retrieval augmented generation. This is more of an exploration. The project already has more than 350 stars on GitHub. So if you like it, make sure to give it a star. So this video is going to cover some of the updates to the project, and now you can run local models. To give you a quick overview, it's a 3-phase exploration process. Here is how it works. So in phase 1, based on the user query, we scan all the available documents. Now, this system does not use any sort of indexing process. The only pre-processing step that we do here is that we convert PDF and text documents into a standard markdown files using docling. So in this step, we use an LLM or large language model to identify which documents potentially have information relevant to your query. And the way we do it is that we look at the start of the document. So if the query is related to some sort of financial information, we're going to keep documents that are related to finances. Step 2 is what I call a deep dive. In this case, it's going to start reading full documents that were identified as potential documents for containing the information. Now, in this case, the LLM can also identify if there are cross references that we missed, and hence the agent can go back and look at the files that were missed in the initial exploration phase. Now, in the third phase, using that backtracking mechanism, it is going to collect all the context that is needed in order to answer the user question. Now, this way we can answer very complex user questions, which usually are not possible with simple semantic similarity search. Okay, but how exactly does this system work? It's inspired from coding agents like Claude Code, which has a number of different tools that can read raw documents or text files. So this system has 6 different tools for scanning your folders, parsing documents, previewing files, reading. There is regex or regular expression based search across all the files. And we also have the ability to find files by path patterns. The previous version of this system used Gemini 3 Flash, but now I added support for a local model as well. So you will be able to use the Qwen 3 model. Okay, so here's how the overall end-to-end system architecture look like. There is a user interface, but you can also use the CLI if you want to build on top of this tool. There is a backend server layer, which both serves the UI and the CLI. Then there is a whole orchestration layer and a tool layer. Now, this project is inspired from the file search project from Llama Index. So it uses Llama Index for event-driven loop orchestration. The agent has access to 6 different tools that we described before. Initially, I built it with Gemini 3 Flash, but now you'll be able to use local models as well, which are hosted on DGX Spark in my case. I'll talk about that later in the video. And at the end, there is also a document processing layer. This is mainly powered by Dockling, which makes sure that everything is converted into a standard format. That way, when the LLM is looking at the data, it is not coming across multiple different file types and it's going to get confused. Let me walk you through the setup process if you want to run this project locally. Now, there are going to be 2 different branches. The main branch is going to contain the original Gemini 3 Flash implementation. I am going to push another branch, which is going to contain implementation for using local models with Ollama. Now, the reason I'm not integrating the same code base is that with local models, I had to make a lot of adjustments for the model to follow instructions in the prompt that I'm providing. Now, I initially started with smaller Qwen models like the 4B, but based on my experimentations, I quickly realized that even 8B or 14B models are not good enough to follow complex set of steps to do exploration. The one that is reasonably good is Qwen 332B. And even for this, I had to adjust the system prompt to make sure that it's able to follow all the instructions and it's able to use the tools correctly rather than hallucinating the results. In order to run this, I'm using NVIDIA DGX Spark because NVIDIA sent me a unit and it has enough VRAM that it can actually support that 32 billion model. Now, the inference for NVIDIA DGX Spark is on the slower side, but it has one great advantage compared to other consumer hardware. We're going to talk about that later in the video. Here is currently how the NVIDIA Sync setup looks like right now. The system has 128 gigabytes unified memory, which makes it easy to run bigger models. To set this up, we're going to have to clone the repo and then install all the dependencies. For this local version, you will just need to set up these 2 environment variables in the .env file. One is the Ollama host, and the second is going to be the model you want to use. Once you run the installation process, then you have 2 different options. One is to run everything through the CLI. The second option is you can run the UI. I am going to show you how the UI looks like. This is a view of the UI. If you click on the browse, you can select the data source. So I have a couple different dummy files or folders. This has 26 different files. The other one has 11 different files. So I'm going to just select this for the purpose of this quick execution. Right now, it says it's powered by Gemini 3 Flash, but if you're using the local branch, then you can just tell it which model to use. I'm going to show you a couple of example queries. This one is a simple query that needs information from a single document. So we're just looking at the purchase price of this startup acquisition. That right now, it's used 38 gigabytes of the unified memory that is available on DGX Spark, and the GPU utilization just went down because I think it completed the process. Now, this was a relatively simple query. So it looked at a single file, parsed it, and here's the information that it found. Okay, here's another query that uses information from multiple different files. So we are asking about what are the key risks that were identified in the acquisition and what mitigation measures were put in place. Again, we can look at the GPU utilization. System memory remains consistent, and now it's using about 96 gigabytes of that unified memory. In this case, the system actually looked at multiple different files because it needed a lot more information compared to that simple query. And here's the final response that it generated. Now, this query itself took about 4 minutes. So the system is not designed to actually give you real-time information like a chatbot. It's going to be more of a document generation system. Okay, here's another very complex query. In this case, the system took about 14 different steps. That means going back and forth, looking at different files that it identified. And at the end, you can see that it generated a lot more comprehensive answer. Now, a couple of comments regarding the use of DGX Spark. I was able to run a 32 billion model. I won't be able to run that on a normal consumer hardware. Now, the inference is definitely on the slower end compared to something like a 4090 or a 5090. However, you can run much bigger models, and I think I can also run a 70 billion model here. A second thing is that having this larger unified memory also give you the ability to run long context with these LLMs. So in this case, I was running this in 64,000 token context window when it's making those parallel calls. Another experiment that I want to run is what happens if you have batched rather than a single request the way I'm doing right now. I think it will be a good option if you are serving customers. Anyways, this was a quick overview of the system. It's going to be an extension of localgpt. If you're working on a local setup to do information retrieval or exploration like this, and you need help, to reach out. Details are going to be in the video description. Anyways, I hope you found this video useful. Thanks for watching, and as always, see you in the next one.